So as I was saying, this formula here is actually an explicit formula for a geometric sequence. I'll remind you of the pattern. So it goes A1, and then R is the number on the inside, and then n minus 1 would represent the exponent. So it's kind of like giving us clues as to what the n value is. It's just not straightforward. So I'm going to set it up in a different way. So we have a 4 on the outside, we have a negative 1/3 on the inside, and then we have a 10 as the exponent. If you think backwards, to get 10 as the exponent, what would the n value have to have been? Because what you do is you take the n value and you subtract 1, and that gives you the power. So n would have to have been 11 in order to take 1 away and end up with 10. So the n value is 11. Okay, and again, that's just using the ending explicit formula and then what we know about like where the first term, where the r value, and where the n value go from the last lesson. Okay, so now that we have those three things, we can move on. And the next thing that we have to do is we have to write the series in summation notation. So what that means, let me go back real quick, is that means we want to write it with this sigma symbol, okay? So when you do this, start with a sigma, and remember that means add up all the terms, which is what we need in order to do a series, because series means add up all the terms. And then we need a command to tell sigma what to do and where to begin. So you need a value at the bottom. I think in the example it was k, but you could use n, it doesn't really matter. So we're going to tell it to start at the first term, so n equals 1. And then we're going to tell it to start at the ending term. And the ending term, based on the information given up here, the ending term, hold on, the ending term was the 11th term. So we're going to tell sigma to add up the first 11 terms. And then in here, we're going to put the formula, the explicit formula for our sequence. And the explicit formula was actually given in a roundabout way up here. So we're going to use the A1, the R value, and then instead of putting 10 as the exponent, we're going to make this a generic formula by writing n minus 1. So that would be your series in summation notation. But in the directions, it did say to also find the sum, and it would be the sum of the first 11 terms. And again, I know that because we found that the last term listed was the 11th term. So we're going to use the formula that was on the last slide. Actually, let me write the formula down here, and then I'll plug in values. So the formula goes, let's see, A1, and then 1 minus r to the n over 1 minus r. Okay, so we're going to plug in n first. So n is 11 because it's the first 11 terms. A1 is 4, first term. R is negative 1/3. N is 11. And then we're doing 1 minus r, which would become a plus because r is negative. So that would be our setup, okay? This looks really messy. We're going to do like a tiny bit of algebra, but then mostly going to do the rest in the calculator. So I have a 4 out here. 1 minus, I'm just going to leave this as negative 1/3 to the 11th because that's going to be a really, really small number. And 1 plus 1/3 would be 4/3. I guess that's the only thing that we can really do to make this look better. You are just going to now go to your calculator and you're going to very carefully type all this in. I would suggest doing it in chunks. So maybe do the numerator, then divide by 4/3, and then multiply by 4 last, not to try to not overwhelm your calculator. Here is the answer. It should be 3.00 0.001693.5, and that's if I didn't round at all. There is an option, if you have a graphing calculator, there is a summation option. So on a TI-84, you can go to math, and then I think it's all the way down at option 0, and it'll give you like a summation, and then there will be like little fill in the blanks down here where you'll fill in where to start, where to stop, and then you'll fill in like the whole formula, like just like we did. I do think you can also do this on Desmos. Let me pop over to Desmos real quick and see if we can do this there. I'm fairly certain that you can. I know a lot of you don't have graphing calculators, so this may be a good option for you. So go to functions. I think it probably is under miscellaneous. Yep, there it is, summation. So I should be able to type all this in. Let's try. Start at 1, end at 11. I do need to know the formula for this to work, and I probably need to put in parentheses. What was it? -1/3. Third. Parentheses. Whoa. My computer is being slow. -1/3. Parentheses. Good Lord. Okay. To the power of, I think I just have the option to use X. It shouldn't matter. Why is this not working? Well, maybe. I probably need to put this in parentheses too. Come on, Strobe. Okay. Is it going to work? No. Oh, it's graphing it. That's not what I want. Okay, I'll come back and make you a video on this if I can figure out how to do it. I'm fairly certain there's a way that we can do this in Desmos. Let me try one more thing. Oh, there we go. I needed to make my variables match both ends. So, yep, there we go. That's our sum, 3.00, whatever. So it does work. So I just want to reiterate one thing. It is totally fine to check your answers in Desmos or a graphing calculator this way, but you do need to know the formulas. That will be something that I'll be requiring that you do know. You do need to know how to put it in summation notation, and you need to know how to use the formulas. But again, I'm not going to make you do all this math by hand. So once I see that you can plug the numbers into the formula correctly, then you can just use a calculator to do the rest for you. Okay, so let's talk for a minute about an infinite series. So this is a very weird concept because essentially what I'm asking you to do is take a pattern that never ends and add up all its terms. Well, a lot of the time it's going to add up to infinity. Like if I just had a pattern 1, 2, 3, 4, 5, like I showed you before, and I say add up all its terms and pretend like the pattern just keeps going on forever. Well, if I add 1 + 2 + 3 + 4 and I keep going like that, I'm just going to get infinity, right? Because adding all these numbers, if they're all increasing, is just going to add up to infinity. So really we're only going to get an actual sum if you have a series that is convergent. Okay, so this will not work for a divergent series because a divergent series is just going to keep going up forever. This is only going to work if you have a convergent series. So we're going to look at a few examples, and we're just going to kind of think about like how the numbers work and how it would work as a series. Okay. So it says, looking at limits of partial sums, for each of the following series, find the first 5 terms in the sequence of partial sums, and which of the series appear to converge. Okay, so the first 5 terms in the sequence of partial sums. What that means is they want us to find the sum of the first term, which is just the first term, so that's weird. The sum of the first 2 terms, which means take the first 2 terms and add them, which would be 0.11. The sum of the first 3 terms, sum of the first 4 terms, and so on. Sum of the first 5 terms. So the sum of the first 3 terms, let's just do that first. That would be 0.111. The sum of the first 4 would be 0.1111. And then the first 5 would be 11111. So we're just adding a 1 to the end of each digit if I add the first 2 terms or the first 3 or the first 4. And that would continue forever. And it says, which of the series appear to converge? Okay, so we're looking at these sums. If I add up the first 2 terms, and then I add the first 3, and then I add the first 4 and the first 5, we could make an assumption that every time we add an extra value, you're basically just adding an extra 1 to the end, right? Forever. And if you look at this number as a decimal, this would just be 0.1 repeating, right? 0.1 repeating. And I don't know if you know this, but 0.1 repeating is equal to a fraction. Kind of think like 0.0 or 0.3 repeating is a third. Well, 0.1 repeating is 1/9. So essentially what we're saying is that this series, if I add up all these terms to infinity, the series is going to eventually get closer and closer to 0.1 repeating, which is equivalent to 1/9. So this series, we want to just describe and say the series will converge to 1/9, or you're welcome to call it 0.1 repeating. Okay? The series converging is different than saying the sequence converges, because series refers to adding all the numbers in the pattern, whereas sequence is just looking at individual terms and what they are doing on their own. Okay, so I'm going to go back and say, look at this. If I just took out the plus signs, right, and I had a pattern that was 0.1, 0.01, 0.000001, whatever, the individual terms on their own are actually getting closer to 0. Okay, so the sequence converges to 0, but the series, when we add all those numbers, converges to 0.1 repeating.